This is second video in the series of videos talking about potential energy. So in the last video we talked about the idea that potential energy is actually better called potential for energy and is virtual concept. It's introduced for making law of conservation of energy work, and the way we do that is we say delta K plus delta U equal to 0, and we also told that delta U is nothing but is minus work done by the gravity. So that's by design, that's the way it is. Now in the previous video we talked about a very simplistic case wherein as a ball it's falling down, and we said, hey, the force is Fg, and this force Fg is, we considered it as constant, which is mg, but in reality this is not mg. This is because gravity is it changes as a function of r, right? And it's a vector quantity, and it changes as a function of how far away you are. So in this video we're going to extend the same idea and see how it fits in. So the ball is falling from I to F, and which is from A to B, and if you plot this force graph, since the force is acting downward, so you can say that force at the distance RE, which is the radius of Earth, is G mm by RE squared, and it falls 1 over R squared. It falls 1 over R squared, right? And this is my initial point, and this is my final point, right? In the previous case we assumed that at close to Earth surfaces the gravitation force is going to be same, right? It's going to be uniform, but that's not the case. Of course, this is your force and this is your distance. This is your distance. So the work done by gravity in moving from I to F is this. This is your work done by gravity, and this is work done by gravity in moving from I to F is integral I to F minus Gmm by R squared into dr, and that amounts to Gmm by R F to I, and that is Gmm into 1 by Rf minus 1 by Ri. So this is the work done by gravity, and we can infer a lot from this, and that's so corollary 1. So the work done by the gravity in moving an object from R to infinity would be equal to Gmm into 1 by infinity minus 1 by R. That's minus Gmm by R. So this is the first corollary. And also the second corollary is the work done by gravity from I to F is a function of Ri and Rf, right? So what that means is that if this is your I and this is your F, it's only a function of Ri and Rf. You could have come any path, right? You could have come to this position through any path. You could have come like that, or any path. So the work done is independent. The work done is independent of path. And in forces where work done is independent of path, we call it as conservative force. We call it the conservative force. So in a conservative force, the work done is independent of path. So that's your corollary 2, right? Your corollary 3 is for small height, that is, your Ri is Re plus H1 and Rf is Re plus H2, and H1 and H2 is way smaller than Re, right? Your work done by gravity is going to be gmm into 1 by Re plus H2 minus 1 by Re plus H1, and that's going to be equal to G mm H1 minus H2 into Re plus H1 into Re plus H2. Now, since the height is very small, we can approximate this as gmm into delta H by Re squared, and your gm by Re squared is a constant. This quantity is a constant. This is a value of gravitational force near Earth, so you can say that at Earth it's mg delta H. So for small height, is an mg delta H is an approximation, and associated with this corollary is, or rather we may call it corollary 4. Corollary 4 is your Wg is equal to minus delta U, and we know that by definition, or the way we saw in the previous video how we use this idea to come up with law of conservation of energy work. So this is nothing but gmm by into 1 by Rf minus 1 by Ri, and that's equal to minus of Uf minus Ui. So this implies, so you can take this quantity here and this quantity here. So this implies that your U of R is minus gm m by R. So this we call it as potential at a point R, and this is nothing but, this is minus gmm by R is in corollary 1. We found out that it's nothing but work done by gravity in moving an object from R to infinity. So this is what we said in corollary 1. So I can also say that minus gmm by R is nothing but work done by gravity in moving from R to infinity. So this is a very important observation, which is potential at a point is minus gmm by R, and work done, or you can also call the potential at a point R. So if you have a Earth here and you have this object here, and so you can say that the potential of this object, the system, the potential of this system, right, in this system, right, the potential, and this is at a distance r, right, at a distance r from the center of the Earth. So the potential of the Earth ball system is minus gmm by R, and that is nothing but the work done by the gravitation field in moving an object m from distance r to infinity. In general, we can, since we know that delta U is equal to minus work done by a conservative force, and if we say that, hey, let UF be equal to 0, then we can say that, look, if UF minus UI equal to minus work done by the conservative force from a distance I to a reference point, a reference position. A reference position is a position where U equal to 0, right? So in this particular case, that R can be infinity, right? So we get this goes away, right? And so your UI equal to work done by conservative force from I to from a point I to reference position where U equal to 0. Okay, so, or you can say in our case, if you say UR equal to minus GMM by R, which is, this is the work done by conservative force in moving object from R to infinity, which is our reference position. So this is our very general thing, and this you can apply this for any conservative force. This definition of U, which is work done by conservative force. U potential is nothing but work done by conservative force in moving an object from that position to a reference position where U is